We are Yingdong and Changming from Shanghai Tech University. Today we are excited to present our work, Dissecting and Mitigating Diffusion Bias via Mechanistic Interpretability. This research was a collaborative effort with our colleagues from Shanghai Tech University, Stony Brook University, and Tencent PCG. Diffusion models have shown incredible power in generating diverse contents. However, as the image illustrates and as many studies have shown, these models often perpetuate and even amplify existing social biases related to gender, age, and race. These biases aren't just academic concerns. They can lead to real-world harm by reinforcing stereotypes and deepening inequalities. Current methods to address these biases typically follow two paths. One involves training from scratch or fine-tuning models, which is resource-intensive and can hurt the model's original capabilities. The other focuses on guiding the generation process, but often risks overcorrecting or distorting other important attributes in the images. This led us to a fundamental question. Can we look inside these models, understand the mechanism causing biases, and use that understanding for more precise mitigation? To answer this, we introduced Diffusion, our framework designed to dissect and mitigate diffusion bias. It operates in three key stages as visualized here. Our method, like some previous work, targets the hidden states within the UNet architecture, specifically focusing on the bottleneck layer. This layer is known to be a rich semantic space, making it a prime candidate for our analysis. A key challenge is that the individual neurons are often polysemantic. They can respond to multiple unrelated concepts. To address this, we employ key-sparse autoencoders, or KSAEs. As shown in part A of the diagram, the KSAE learns to reconstruct the original activations from H from a sparse high-dimensional representations S. This disentangles the features and making them more monosemantic and easier to interpret. Once we have sparse semantic space, we need to pinpoint which features correspond to specific biases like gender or age. We achieve this, as shown in part B, by training a lightweight classifier fx and on these sparse features, and then use a gradient-based attribution method. The attribution score defined in equation 6 essentially tells us how influential each sparse feature is in producing a particular biased outcome. With the biased features identified, we can then intervene as shown in part C. Instead of broad edits, we can precisely adjust the activations of these specific features, either by scaling them or adding an offset. This allows us to suppress or amplify the feature's effect, thereby controlling the level of bias in the final generated images, as hinted by the transition from female to male.
For experiment, we evaluate difflens on two pre-trained models, P2, an unconditional model, and the well-known stable diffusion V1.5. We compare our approach against several strong baselines, including activation-based methods, latent editing techniques, and fine-tuning. Our key metrics were fairness discrepancy to measure bias level, FID for image quality, and clip I and clip T for semantic consistency. So how effective is difflens? The results are very promising. Looking at the tables for both P2 and stable diffusion, difflens consistently achieves good bias mitigation, that's low FD scores, while crucially maintaining high image quality and semantic integrity, which is shown by good FID scores and high clip I scores. The key advantage of difflens is its precision. These images show that our methods accurately identifies and modifies only the target bias features, while other methods might distort non-target attributes like eyeglasses or facial expressions. Difflens preserves the overall image semantics remarkably well. The precision translates directly into fine-grained control. You can see smooth and consistent transformations along gender, age, and race axes, preserving semantic features throughout. The plots show difflens achieving a wider range of bias control, from balanced to highly skewed ratios, while maintaining superior image quality and semantic coherence compared to other methods. Especially at more extreme ratios, we achieve overall stable results. The qualitative results below shows our stable control of bias. Beyond single attributes, difflens also allows us to explore how multiple features interact. Here we see examples of controllably attributes like male and old simultaneously. We can isolate and manipulate each attribute independently. Our work builds upon a rich body of existing research in bias mitigation, diffusion models, and interpretability. In conclusion, DiffLens introduced a novel way to mitigate social biases by dissecting internal model mechanisms. By disentangling features, identifying those responsible for bias, and precisely intervening, we achieve effective debiasing while preserving image quality and non-target attributes. Thank you for your attention. For more details, please scan the QR code to visit our project page.